Thanks everyone for coming, and it's a pleasure to be able to share my work in recommender system and graph deep learning in general to this audience. I'm very glad to have this opportunity to be here and meet a lot of people. So this was the work that got the award was work that was actually done back in 2018. So that was like quite a while ago, but since then, graph learning and graph structure-based deep learning has grown so much, and it's actually becoming a very interesting direction for a lot of people. I would like to basically go over some of the techniques and innovations that we've done in that particular work, and also want to spend maybe half of the time talking about what's graph learning be in the next few years, especially in this context of foundation models, large language models, how this graph or in general structured data help building these large-scale pre-trained AI foundation models for various kinds of downstream applications. All right, so I guess we'll get started. Yeah, let's start by introducing this modality in general. I know that there is probably a mix of audience who's like from undergrad all the way to like researchers and advanced machine learning people. So, but let me just start kind of a very basic. Graph is very typical kind of modalities, right? Lots of real-world scenarios are being represented in this abstract concepts of nodes that are interconnected through edges, right? And there are features on nodes, on edges, on graphs as a whole, subgraphs, and so on, right? It's been used in many things like knowledge graphs, food webs, different physics kind of applications, computer networks, disease, traffic. I can go on and on, right? There are a lot of things like social networks, and in particular, for example, recommended systems was one of the applications as well. And again, I'm showing a bunch of these vision applications, molecules, and things, across science and engineering, in various different disciplines, all of which are organized in this kind of simple concept of relationships between entities, right? And being able to perform machine learning on these kind of natural data that exist out of these abstractions in science and engineering is a critical aspect of AI, especially in the domain of science and engineering, right? So these are particular modalities that are very interesting to learn about, right? So related to the work that I'm supposed to present, right? It's a recommender system, which can also be formulated as a form of graphs, right? You have a bunch of users, and then you have a bunch of products or videos, whatever things, right? Posts, whatever things you want to recommend. Right? You think of it as like Amazon, you buy things, right? Or think of it as like TikTok or whatever you want to recommend videos to users, right? And all of these can be abstracted into this concept of nodes that are connected through user actions, right? The user can buy stuff, can view stuff, can dislike, can like, can post various other actions, and all of these are being represented as edges. And the machine learning tasks here are very simple, right? So you recommend items, right? Say, what are the future items that the user might be interested in looking at, right? Or it could be like classifying users. Let's say, I want to identify fraudulent activities. I want to identify trolls in the system, right? I want to identify malicious items or malicious users in this commercial platform. And there are other kind of applications that are equally kind of large scale. I remember large scale is something that we kind of focus on a lot in this talk. Things like social networks, right? You have all these kind of social networks, and it's basically like connections between people. And again, you can formulate tasks like recommending friends, recommending items, posts to people on the social network, right? Another scenario that I'm personally quite interested in is also equally large scale, that is academic knowledge graph, which consists of papers, authors, institutions. Papers have a lot of text attributed features, right? Talking about the content. This is especially relevant in building foundation models nowadays because a lot of these models are, say, large language models, right? So they kind of encode text information, but a lot of times they don't really encode the relationship between documents. As a result, finding the relevant document and finding the relevant knowledge in this vast amount of like large-scale database of papers or domain-specific materials is going to be extremely hard, right? So researching this particular field will also be interesting, right? Recommending relevant papers and things is going to help features like deep research in large language models. Right. And finally, we have knowledge graphs. Right. The entities can also be very big, like close to 100 million entities, and those are basically concepts that are related by different text attributed relationships, as you show an example on the right. And a lot of tasks can be formulated as well. Actually, later on in the future directions or in some ongoing works, I will present some of our more recent works on using knowledge graphs to enhance and avoid hallucination for large language models. Okay, but what are in common among all these examples that I've shown? Like they are extremely large scale, right? Recommender system is about like billions of items and hundreds of millions of users. Same thing goes for social networks. Same thing goes for I'd say all the archived papers on the internet. The same thing goes for knowledge graphs, right? They are extremely large scales, and being able to perform representation learning or machine learning in general on these extremely large graphs using deep learning techniques has been quite a challenge, and it's been something that people have studied back then, right? It's 9 years ago until even recently, right? Where this kind of foundation model research on large scale relationship databases are still quite important. All right, so let's start simple. A simple question that we considered back then was, in particular 8 or 7 years ago, right? How do we take advantage of this kind of relational structure? With all these use cases that are also very large scale for better machine learning predictions, right? Be able to perform all these tasks through AI, right? And prior to 2017, deep learning full boxes was primarily designed for very simple or very regular things. I would argue that even now, right, this is kind of the majority of what people kind of focus on, right? And then there's image, which is kind of a grid. If you think about this, right, like the grid structure, it's always like width times height, right? It's very regular, right? And things like vision transformer, kind of convolution kind of works well in those domains. Similarly, text and speeches, they are also very regular, even one-dimensional, right? I would say, it's basically a sequence of tokens, right? And things like recurrent neural networks, which was popular back then, or even transformers, which are relevant now, right? They all deal with this kind of sequence or sequential structure, right? So graph is particularly different, right? It's not regular. If you look at a graph or a network on the left and versus an image or a sequence of words on the right, you can clearly see the differences, right? There's no node ordering, so this invariance to ordering of nodes, right? Without this coordinate kind of concept or the position of your word in the sentence, without this kind of concept is particularly difficult. Multimodal features are also kind of important because nodes and edges have their own high-dimensional features, or even text attributed features, image attributed features that you need to take care of. So yeah, so it's kind of different, right? And the question that we kind of study is how do we develop neural networks that are kind of more broadly applicable, right? So that we can use these graphs as input and make predictions on top of that. Right? So in the context of a recommender system, what's the task is going to be is related to this thing called link prediction, right? So these blue edges are those past interactions. Maybe the user bought a bunch of items, right? Or the user likes certain videos, right? And then what we want to predict is the green thing, right? Which is if I were to show another video to you, you will be super interested, right? So that means your recommender system is good, right? Otherwise, it's a bad recommendation. In reality, it's a much more complex than that. But this is a very simple primary objective. So what's the task would look like, right? or what the overall training framework would look like in almost all the recommended system is like that. So let's say it is one type of recommendation where you recommend similar items, right? The user looked at item A, and we guess that he might also be interested in item B, right? So the task is basically of a contrastive in nature, right? So on top, that's a good recommendation because it looks similar. The user bought something on the right, and then it's more likely that it's kind of interested in this thing on the right? Whereas the shirt is kind of irrelevant, and maybe the user won't be interested, right? So that's a very simple or even naive definition, but starting from that definition, the objective is very straightforward, right? The goal is that we embed all these items, all these users into a hidden embedding space, right? So, into a vector space, such that distances between the right recommended item and the left item that the user see is very small, right? For a correct or for a good recommendation, whereas for a bad recommendation, the distance in a vector space should be very big, right? So then you can clearly use distance to know what items to recommend, right? So that's the intuition. And how do we exactly generate these embeddings such that this kind of property holds, and we can use that for recommendation? That's kind of the topic that we studied in this paper called Pinsage. Okay, so this is the paper that I'm supposed to talk about, and I also listed one of the relevant paper, which is kind of also building on this. And this is a first billion-scale graph-based recommender system. Algorithms have been used a lot since then, being implemented and deployed in real-world products in some of the big tech industry leaders from Google, Amazon, Pinterest, Snap, Facebook back then, right, and financial ByteDance, and from what I know of, right? So it's an interesting paradigm, and this is all kind of based on this idea of message passing in graph neural networks, which we did in one of our previous works. So the intuition is that in order to compute the vector representation for nodes in the graph, I want to collect the nearby neighborhood information, right? I want to collect all the information of your multi-hop neighbors and aggregate them into a vector that can describe the neighborhood. And that vector is produced by aggregating information through a deep neural network, right? So this is a quick example, right, for people who are less familiar with GNNs. Actually, how many people are familiar with it? Maybe if oh, no one? Anyone raise their hand if they know about this stuff? Okay, I should go a lot slower. So in order to compute the representation for, let's say, this yellow node in a graph, I want to use neural network to aggregate all the previous information, right? So the first hop, which is very simple, is that what are the information that is contained by the neighbor of the yellow node, right? And those could be, let's say, if the yellow node is an item, then those red and green, and those can represent like related items that were co-purchased by some user, right? And we aggregate information through these arrows, and in practice, these arrows are parameterized through deep neural networks, and then aggregated into a computing representation for A, right? So that depends on the premise that we know the representation of the red node, green node, and blue node as well, right? And how do we compute them? We kind of do this recursively, right? So in the second layer, we further aggregate the neighbors of these red, green, and blue nodes respectively, and again through neural networks, and that way we get the representation, right? So we can do this indefinitely. I'm just showing like 2 layers, right? But in practice, we can do this recursively over multiple layers, and that defines the depth of the graph neural network, right? And there's always going to be a base case if you do this kind of recursion, right? So what is the base case? It will just be a certain layer where we decide that we no longer want to aggregate, but rather we just use the input feature of the node, right? So in the context of recommended system, maybe it's about the basic features or basic properties of the item in the online platform. In cases or in scenarios where there isn't a input feature or there isn't a property feature for every node, then we would just use constant vector for random initialization. All these are possible ways. Okay. All right. So yeah, so this is the way we compute representation for every node. And if you kind of expand it out, you see this kind of diagram, right? We can do this same process for all the nodes. Okay. As you can see, each computation graph here is different, obviously, because each node will have different kinds of neighborhood structure, right? So they all look very different, right? But then the computation itself can be parallelized, and we have various ways to make efficient use of GPU to be able to do this. And in fact, this is super critical, and that's also one of the key challenges that we were trying to solve in the paper that we did. Okay. All right. So yeah. So let me just go into a little bit into detail, right? So we mentioned this diagram where the representations of every node in this relational structure is done through message passing, which means I pass information of the nearby node and I aggregate them into the representation of the current node. And all these individual arrows are basically, you can treat them as either linear transformation plus some nonlinearity, or in general multi-layer perceptron there, right? And then this box is basically your aggregation. Right? The simplest aggregation could be just summing all of them together, right? But we also can develop more complex aggregation scheme to kind of collect all the information of your nearby node and merge them into one single representation. Just to kind of make the terminology clear, this example is a two-layer graph neural network, and the second layer representation is being computed here from the first layer representation of the neighbors, which are in turn being computed by the zeroth or the input layer of the two hop neighbors. And these input layer features are basically the input features, the properties of the items. Okay. All right. So there were three highlights of this kind of architecture that we try to solve in this paper. The first is that we want to make it efficient. And the second is that we want the representation to have high quality. So what kind of objective do we exactly use to compare and contrast different items in order to recommend you the best item, right? And the third one is related to inference time. We want to, once we train such a billion-scale recommender system, we want it to be able to inference and make recommendations as fast as possible with as few latency as possible. Right, so let me just summarize what each kind of innovation or novelty highlight is for that paper. First of all, we would want to talk about neighborhood sampling, and that's a key technique to ensure that this whole thing works for billion-scale items. Right? One thing that we can do is that, first of all, we can leverage GPUs for all kinds of applications, all kinds of graph neural network computations, similar to all the other deep learning algorithms, right? What we do is that in order to compute the embeddings for all the nodes in a graph, we select a few of these and form a mini batch, and then we do a computation for this mini batch of nodes by looking at their neighbors and their neighbors' neighbors and so on, right? And finish all these computation tree in one mini batch, right? After that, we do the standard thing, right? Compute the gradients, do backprop, right? So that's the typical machine learning stuff, right? And once we finish computation of this one mini batch, we go to the next mini batch, and so on. And then the optimization is done to a stochastic gradient descent. Okay, this is a standard paradigm, but you already notice what the difference is compared to standard, deep learning training scheme, right? Because we not only just need the mini batch of nodes, we also need the neighbors, and we also need the neighbors' neighbors, and that's kind of what makes things very expensive. Okay. All right. So we consider this stochastic gradient descent, right, which is the essential thing we use to train almost all the deep learning algorithms, right? And looking at, remember we're looking at this mini batch. Mini batch of stuff, so which requires all the nodes, and then all their neighbors and their neighbors' neighbors, and so on. But in general, if you want a k graph neural networks of depth k, then you need this k-hop neighborhood to be able to achieve that, right? And that's what gets things very expensive, because for every example, for every node in your graph, you need to gather the entire neighborhood of that node and put that into the mini-batch, right? And you already know what that implies. It's going to be expensive, right? Because a node, for example, let's say a popular item or popular user, it might have like hundreds of or even thousands of interactions and thousands of neighbors, and not to mention neighbors. So it's going to be very expensive. Okay. And in general, right, in worst case, there could be exponential growth with respect to the depth, right? If you look at the multiple neighbors that are multiple hops away, chances are your mini batch is going to be huge because all your neighborhoods are going to be huge, right? That's not very good, okay? And especially for hub nodes, right? If you have a super popular item, a super popular video, right, then this entire thing just going to take forever, okay? So a very natural thing that we do in those cases is by sampling, right? So a very naive way of sampling is done through, say, a uniform sample. So for every node, I look at, say, all my neighbors, but instead of choosing all my neighbors and aggregate them through neural networks, I uniformly sample a bunch of them and then aggregate, right? And the same thing goes for the second hop and third hop and so on. But we actually realized that is also not a very good way of doing aggregation, because at every step, you are, first of all, discarding some of the information, and you don't know which of your neighbors are more important to you, right? So you want to aggregate things that are going to be more informative about the property of the current item you want to recommend, right? So what we instead do in that paper is through a random walk, right, to identify important nodes and important neighbors to aggregate, right? Instead of getting all the neighbors, I'm going to aggregate a subset of important nodes, and those important nodes are being computed through random walks. And random walks is very simple to define, right? Starting from a node, you have some uniform distribution to go to any of your neighbors, and then you iteratively do that same process again and again, right? That's a random walk. And what's interesting, right? There is this thing has already been used, in a lot of different contexts, and notably in founding of the company Google, right? They use random walks and personalized PageRank to compute importance of nodes on the entire internet, right? So that's going to tell you, how important a website is by looking at the nearby website and looking at through a random walk. Right. So I'm not going to the mathematical details here, but just to know that we can perform random walk and understand what are the most important nodes that are nearby, and we select those nodes. We sample these nodes in order to aggregate information. Right. So in order to get the information about the current node, I'm going to pick the most important nearby nodes through random walks. Okay. The second type of techniques that we thought was super critical in success of such recommended system is called contrastive learning. Right, this was the diagram that I showed before. Right, in order to recommend items, I want items that are similar to have similar embeddings. Right, so now at inference time, if I want to recommend things for this item, I'm just going to pick the nearby embeddings. Right, so that's a very simple thing, and the task here or the objective here is also being written, right? So I want the recommended item to be close together, and then things that don't get recommended to be far away. Okay, so that's called contrastive learning, and that was very popular also. It's also very popular now, right? It's a very common technique. But this is not just restricted to graph data. Contrastive learning is in fact used for all kinds of pre-training in multimodal settings. Okay, even like now, text to image and everything. Right? So here's an example of image modality because I thought it's more intuitive, but the principle is the same, right? Basically, we embed all these entities, in this case images, into embedding space, such as similar items are being embedded close together, and then we push apart things that are different, right? So here, these two cats are kind of similar. These two, I don't know, tiger or whatever, being embedded similar, but then I push apart the cats and tigers so I can distinguish them in the embedding space. And yeah, so that's the same thing, right? Two cats are being pushed together in terms of embedding space, and then the cat and dog are kind of pushed far away, right? And that push and pull is done through this info NCE objective. Looks complicated, but it's really very simple. The part in the numerator is the positive example, which means two cats, right? You want them to be as similar as possible, so you maximize that inner product between them, right? And then everything else that is not similar, you push them very far away, right? These are called negative examples. That's in the denominator, right? You want them to be as far away as possible, so that this entire objective with a negative sign in the front is minimized. Okay, and B here means the mini batch. So it's really a very simple objective here. Okay. All right. So what's new, I guess, or what's important in that paper? So in that paper, we realized this one thing. Picking the positive is very straightforward. Basically, like whatever the user ended up choosing, right? That's your positive example because that's what the user likes, right? But picking the negative example is what really makes the performance kind of differ, right? What kind of makes a difference, right? So what are the kind of negatives out there given one example, right? So here are some intuition, right? On the left, there are this is ranked by similarity, right? Obviously. So on the left, there are these items that are completely different from the input, right? It's completely irrelevant. These are called easy negatives. What do we mean by easy negatives? It's basically making the model super, or it's super trivial for the model to distinguish them because they're completely different, right? And in the middle, there are hard examples, and those are the ones that are kind of a little bit tricky, right? So they look like a cat, but they're not really a cat, right? So they're somewhat similar. The model kind of needs to really pay attention, needs to focus, right? Needs to have a high capability in order to distinguish them, right? And then on the far right, these are negatives that are really not really negatives. These are exactly cats. So like if we ended up sampling those kind of stuff, that's false negative. That's also not good, right? But of course that's bad. But what about these other two, like easy and hard negatives, right? So can people guess, right? How whether it's which kind of examples are going to be more important for model training? All right. I think a lot of people would guess that hard negatives are actually beneficial, right? Because easy negatives are too trivial. The models don't need to pay attention to distinguish, right? It's like it's not really learning anything, right? But hard negatives is really those that kind of push the boundary and pushes the capability of the model, right? In order to be able to distinguish very similar things, right? Understand the subtle differences between cats and tigers and so on, right? So that's also the kind of intuition that we want to bring, right? Which means that when we sample the positive example, it's basically the user's recommendation. There's no question about it. For example, negative examples, we want to sample those that are kind of hard, right? So those are similar, but not exactly the same, right? And we want to say like, hey, the model, you need to kind of distinguish these negatives from the positives, from what the user is really interested in. Okay, so that's the objective, and in that paper we indeed tried this curriculum learning with hard negative pairs, right? So be able to supply examples that are similar but are not what the user likes, right? And continue to train the model to have the distinguishing power so that it can always recommend, or it can learn to recommend things that the user really likes. Okay, so you can see it as a teaching the student or teaching the model to be more kind of to have more distinguishing power. All right, so yeah, so these are different ways to create negative sampling. I'm going to skip over these, but in recommended systems, what we basically do is also through this thing called random walk, right? The idea is very similar to how we do sampling. We want to sample those things that are close enough, that are important enough, but not really the most important thing, or not really the most relevant thing, and we use that as a negative example to train our recommended systems. So through random walk, if those nearby neighborhood nodes are the most important, I'm going to treat it as positive examples. That's what we want to recommend. And if it's like, let's say rank 50 to rank 100, they are somewhat relevant, but not really the things that the user like the most. We treat that as hard negative examples, and we train it through contrastive learning. Okay, so here's another example of recommending, I guess, images, right? The query is on the left. Positive example is exactly like the query. Random negative is completely irrelevant, right? And then the hard negative is somewhat close in style, but not really what the user likes the most. So yeah. All right, so we have some follow-up afterwards in 2023 that just extends the idea of this hard negative sampling, contrastive learning in those large-scale pre-training for vision models, language models, and graph models. But that's sort of an extension, just an example saying how this idea can evolve across different modalities. Here are some examples. So we had some benchmarks here. On the left is what's the item that is being shown to the user, and different roles are basically different qualities of recommender systems. Some of the baselines only use visual features. Some of them use text feature, annotation features, and so on. Some of them just use pure relationship graph features. But our model is able to kind of incorporate all these individual features through this message passing paradigm and produce things that are both semantically and syntactically relevant, right? Similar in terms of appearance and in terms of content. All right, and the last part I'm going to go very briefly because it's very engineering heavy. We basically formulated this MapReduce pipeline to kind of make the inference kind of seamless. So we have a very high like large-scale compute, CPU compute, to be able to pre-process all these neighborhoods and supply node features and do all the pre-processing, graph-based random walks, and so on. All of these are done through CPUs, and then GPU is going to take that and then do your deep neural network, backprop optimization, and so on, right? And a lot of time is being spent on CPU, a lot of time is being spent on GPU, but we have this parallelization scheme. So while the GPU is computing the optimization for the current mini batch, I'm already using CPU to do pre-processing and do these compute for the second batch, right? So we basically do that alternating and thereby hiding all the computation overhead necessary for doing all these random walk sampling, neighborhood construction, and everything for all these graph operations, right? So just to summarize what we covered. So it's basically a recommender system that is representative of a variety of real-world applications, from short videos to commercial platforms to social networks. Right? And the insight from this paper was about effective neighborhood sampling to perform message passing paradigm, and contrastive learning active sampling to ensure high-quality recommendation. And finally, we have good test time techniques to ensure that this entire system can run smoothly, even with billion-scale products and recommender systems. And a lot of future directions, which I will mention a little bit as well. And since then, the paper had 1,000 citations and used in many real-world industry applications. And here are some examples where such kind of algorithm has been used. How does this paper, or I guess in general, graph learning inspire foundation models, and which is what we see a lot nowadays, and how does this idea of building those large-scale pre-training foundation model improve graph learning and improve applications in recommender systems and many other graph structure data machine learning in general? Okay. So foundation model paradigms, I guess here's for this kind of graph modality, generally looks like this. We have a tremendous amount of unsupervised data in graph or maybe multimodal in different kinds of modalities, and we pre-train it with some encoder, or maybe it's a decoder only, right? We pre-train it with self-supervised losses, could be contrastive, could be autoregressive, and many other things, right? And after we do the pre-training, we can directly bring those encoders to a specific downstream task, right? So this part is frozen, or usually frozen, and we can just tune like certain task-specific heads. With very few examples, we can train it very well, right? So the majority of the computation and learning burden is actually in the pre-training stage, which kind of aligns with the foundation models in almost all the modalities. Yeah, so how does this going to be applied in graph structure data? This is an extremely challenging problem that we don't have a good answer to, even in recent works and recent research. Right. The key challenge is that unlike text or unlike image modalities, these kind of structured data, it's not just specific to graph, right? It's also true for tabular data, for time series, and all these kind of structured data. The domains are so different, and the feature spaces are so different that it's very hard to build networks where all these domains can be trained simultaneously together and giving us benefit to downstream tasks. Right? Imagine that you have graph data that are, say, recommended system, but then you also have graphs about proteins, you have graph on social networks, on molecules, on everything, right? So you have all these different graphs in extremely different contexts. They have completely different features, and now the question is, how do we pre-train a foundation model, like a large-scale model that can utilize and understand all these different structures, right? So it's extremely challenging. The way we, so this is actually a submission that we did this year. The way we kind of did it is that we pre-train on a bunch of objectives that are very specific to understanding the structural property of graphs, ignoring all these feature information in the input data sets, right? And the idea is that we build some kind of pre-trained structural and positional encoder for all the nodes in the graph, such that it can be transferred into completely different domains, right? And in the downstream task, all we need to do is to bring this structural encoder, right, that encodes all the structure of the graph and combine it with the feature space thing, and then do some kind of few short learning to get the answer. So here are some objectives that we designed that are all very specific to graph itself and kind of irrelevant to or agnostic to the actual domain that is going to be applied in downstream tasks. Include things like regressing on shortest path distance, counting different kinds of motifs, detecting communities, graph contrastive learning. So these are like very kind of inspired by large language models, right, which just simply uses autoregressive learning. Here we are designing these objectives that are very simple and that are very fundamental to understanding graph structure, and use that to pre-train a model that just focuses on understanding structure itself, right? And in terms of classification of these objectives, there are things that are node level, right? Just try to understand individual nodes in the graph. There are edge level things, understanding relationships, graph level things, or subgraph level things, understanding the entire structure, right? And you can also classify them according to what kind of objective, right? Or it can be contrastive, which is what we just mentioned in the recommended system example, or it can be reconstruction, which is what the large language models and stuff are doing, right? So these are the objectives, and we have ways to combine them, but that's detailed. But loss is basically like a combination of all these different individual losses, and now we're able to train it end-to-end with all kinds of graph structure, with all like in all kinds of different domains, from molecules, science, physics, all the way to recommended systems, social networks, citation graphs, and so on, right? And how is it going to be used? This is an example. So we train this thing called structural encoder, and that thing is being frozen once after pre-training, right? So in terms of downstream application, if it's a numerical feature, we simply concatenate this numerical node feature with the pre-trained position encoding or structural encoding that is already frozen, and then we do some message passing at the end, like standard graph neural network, and then we predict the downstream task in a few shot setting, right? And let's say if it's text attributed graph, in that case, for example, every node, it contains all kinds of different text features, then we can simply project all these pre-trained encodings using a multi-layer perceptron into like graph tokens, position tokens of the graph structure, and then we combine with text tokens, which are individual documents, and then we fine-tune the large language model to combine both things together to make our prediction, right? So it's kind of flexible. You can, whatever kind of features, you'll be able to use that as a universal encoder for graph structure. Okay. We get state-of-the-art state-of-the-art performance in various benchmarks, and we show something like, as long as you add this positional structural feature that we pre-trained, you are able to just get performance improvement across the board. So it's kind of like kind of free improvement once you pre-train this thing for any kind of downstream task. All right. So we also showed its improvement on Llama. So this is a kind of a recommended system kind of task. And by adding this graph structure information to natural language features of the item, we're able to improve performance on this product recommendation scenario as well. Okay, so that's kind of one direction I think are very interesting, which is how foundation model and these pre-trained, the idea of pre-training and self-supervised learning for diverse downstream tasks, and that kind of idea can be used to improve machine learning for this kind of graph structured data. And we also can see it in another perspective, right? Which is how we use graph and how we use this kind of relational reasoning, the idea of understanding relationships, and how that can improve large language models. So we kind of help them in both ways, right? So the reverse is also true. Here's an example. Again, it's kind of a work that we've done in recent months. So basically, graph helps LLM with better retrieval and avoid hallucination stuff, right? So here's an example where a question was asked and large language model is supposed to reason and answer a question, but sometimes it hallucinates and it provides the wrong date of birth, for example. No, not date of birth, like wrong date for this movie or whatever, right? Instead, what people do nowadays is that they kind of keep this kind of knowledge base, right? And instead of directly using the language model to generate your answers, it's going to retrieve relevant information from the knowledge base and use that as a supply to your large language model, so that the large language model basically tries to answer given the retrieved document, right? Or retrieved information. Right, so retrieve augmented generation is kind of popular, right? It helps reduce hallucination and improve the capability of LLMs, and that's kind of commonly known, right? So another question is, what happens if your knowledge base is in the form of a relational structure, right? Like a knowledge graph, right? Where different entities are related to with different events and different relationships, right? What if your knowledge base is like that? And in fact, a lot of times knowledge bases are in the form of a graph structure. And that is especially important in things like biology and other kinds of sciences, right? Knowledge are organized into graphs, and existing works that do this looks a little bit complicated, but you don't have to look into this. But existing work does this by training a graph neural network retriever. So given the structure, it's going to retrieve what are the most important entities and facts in the knowledge graph, and then use it to feed it into large language model. So it's kind of a two-step process. It trains a retriever, retrieve the stuff, and then it brings that into the large language model, right? So the obvious issue with this kind of thing is that it's a two completely separate pipeline, which means that first of all, you need a specific loss for the graph neural network retriever, right? And that is not directly or nicely end-to-end integrated with the large language model. And the second thing is also directly consequences that you need a ground truth retriever. You need to know that for this question, this is the right fact in the knowledge graph that answers the question. But a lot of times, all you have is the answer, but you don't know where in the knowledge graph is that stored, right? So that's very common, right? You know the answer, but you don't know what is the ground truth retrieval, right? In that case, existing methods like this will also fail. So yeah, so the idea is that can we do both things together? Can we have our large language model and have our graph neural networks between end to end, right, forming a kind of a holistic architecture that balances both part of the retriever and the language model reasoner. Okay, so this is the framework that we propose. Everything is being done in one training framework. The backpropagation is done simultaneously for both the graph neural network component and large language model components. It's structure aware, it can generalize and everything, right? So the idea is that the GNN is going to do the retrieval, which helps the language model, and then the language model is going to do reason and provide feedback to guide the graph neural network, say, this is the right thing to be retrieved, or this is not the right thing to be retrieved because I couldn't answer the question. Basically feedback from both sides and helping both sides. Okay. So the overall architecture looks like this. So on the right we have the loss function, right? It's very easy to see, right? Once we break down this loss function, right? The green part is the loss for the large language model. It's super straightforward. It's a standard large language model loss, right? This is like the probability of your answer given your query and given your knowledge graph, G, right? It's easy stuff, right? But we also augmented with a second objective, that is try to train a GNN retriever, right? So this is to say that the purple stuff, if you can see, is exactly the same as the green stuff, right? But the thing to be optimized is different. In the first one, I'm optimizing all the parameters in the large language model, and in the second stuff, condition on the large language model, I'm going to optimize my retriever. Okay, so the parameter to be optimized is different. But this is basically the feedback from LM. So LM is going to say, oh, I'm able to answer this question. Oh, I cannot answer this question. And that is basically this loss, right? How well am I able to answer the question? And using chain rule of statistics, we multiply by another factor, which is the probability or the graph neural network retrieved subgraph or retrieved knowledge given a query queue. Okay, so we have like two different things. And intuitively, you can think of it, right, as optimizing for relevance, which is composed of two things. One is usefulness, which is how useful is the retrieved stuff for the large language model, right? If the large language model thinks it's useful, that's good. Okay, and the other thing is relevance, which is how relevant is the retrieved item to the query, which is exactly what we optimize here. And multiply them together, you get a loss function, and then you train the entire thing into it. Okay, and notice that here you have parameters for LLMs, you have the parameters for GNNs, and everything is being done together. All right, so here's an example of how this is going to use. So I'm trying to wrap things up. Here we have some graph token. We basically want to say that answer the given question, right, using the provided knowledge base, right? So that's kind of a hidden prompt in your large language model, right? And then it's going to supply the retrieved item. So this is being output by the graph neural network. That's going to retrieve all these useful triples from the underlying knowledge graph, and these are the results of the GNN retriever, right? So that part is being appended as tokens into the input to the large language model, right? So large language model is going to see this prompt, it's going to see this reasoning path, it's going to see the question, and it's supposed to answer. Okay, so the answer is going to be based on the reasoning path that is being provided by the GNN retriever, right? And then the entire thing is also done with supervised fine-tuning methods like low-rank LoRa. Okay. All right. So yeah, so that's the method, and we observe that can obtain state-of-the-art compared to other retrieval augmented generation frameworks, and in general, improve large language models. So the method is performance is in red, right? We're testing on Llama 2 and Llama 3, all of which outperform all the existing baselines in this task. So this particular task is medical QA, so it's supposed to answer all different kinds of medical exam questions. Right? And this one is on like general freebase, like web QSP, web questions, internet questions. Right? So here are some case studies. So in the knowledge graph, so here's the question, right? And then the GNN retriever. So if you directly use in GPT-4, you provided a wrong answer, but our GNN retriever is going to find relevant documents and relevant entities through searching the knowledge base, and is going to supply the relevant triples by retrieval. And after that, the large language model is able to answer the correct question. Give the correct answer. Okay. Finally, I'm going to briefly talk about our work on KDD 2025, also this year, which I think is kind of more like an extension of kind of example use case applications where graph and foundation models work together, right? So we built this thing called LitBench, which is basically a data set where it contains any, it's basically more like a library, right? The user is going to ask, oh, I'm interested in this particular field, and this library is going to search you the entire graph of all the academic literature that is related to this field, right? This field can be super complex. You can say, like, give me all the papers and all their citations and relationship between these papers in the field of physics, right? Alternatively, I can ask something like, give me everything, all the papers and citations in this particular intersection of AI for biology, right? You can also do this thing. So it's a super flexible way of obtaining all the literature graph. This is the pipeline, right? And the goal is that we can use it for different kinds of domain-specific fine-tuning. So basically, go into one domain and then train a large language model based on all these documents, and more importantly, the relationship between documents. So what we wanted to convince is that for tasks like say finding relevant documents, finding related works of a given topic, and recommending papers given an abstract, for these things that kind of care more about the relationship between different papers, graph information is super important, and we should use things like graph retrieval and graph understanding, graph representation learning to be able to perform well in those kind of tasks. Right? So here's a demo of what we do, like basically constructing such a domain-specific data set and be able to fine-tune there and answer questions that are specific to that domain. All right, so based on this kind of data set, we can also develop an architecture or develop a model that reduces different kinds of hallucination when answering those domain-specific questions on these kind of papers and their relationships. Okay, and we were measuring, in all kinds of different downstream tasks, like predicting the citation links, generate me the related work given like a topic or given a paper, right? Complete your abstract, given your introduction, generate the title of a paper, and so on. So and then we show that our model that is based on the graph structure can outperform all the existing large language models in these literature-specific tasks, and particularly those that require understanding of how papers cite each other and how papers kind of relate to each other. Right? So this is the framework. I'm not going to in detail, but this is a downstream task, so people might be interested in some of them, right? I think actually a lot of them are quite important in research, right? I think having an agent that can give me all the related works and be able to do a survey would be super awesome. So this is exactly what we do here. Yeah, performance is here. So with graph information, right, citation of how in documents relate to each other, we're able to achieve state-of-the-art in all these kind of literature-related tasks. Yeah, and some visualizations of our performance compared to baselines. And yeah, so finally, I'm going to show a case study where I'm showing one paper with a title and abstract, and another paper and abstract. And then the question is how these two papers relate to each other. If A were to cite B, what will A discuss, right? And this is a ground truth because this actual paper actually discussed paper B, right? So we get the ground truth of what the author really thinks, and we get some answers from GPT-4o, DeepSeek, and so on. And we actually realize that there are a lot of hallucination even now, but we are able to answer all the questions and be the best to be aligned with what the author really thinks about the relationship between these two papers. All right, I think that's all. And I just want to thank all my funding agencies and all my collaborators at Stanford and Yale, various funding agencies and various industry partners that kind of supported all my research in the past few years. And here are the co-authors of the paper that I'm supposed to present. All right, and thanks everyone. Yeah. Yeah, the short answer is that you can use your sample size to control the trade-off, right? If you want efficiency, you only sample very few most important neighbors through random walk, and then if you want better accuracy, maybe you sample a little bit more. And then the long answer is that I think it's sort of also related to the hardware and the infrastructure that we built. Random walk is something that that can be very optimized through parallelization, especially through CPU compute. You can run multi-threads and multiple processes to be able to random walk and accumulate counts for all your neighbors. Basically the number of visits of each of all the random walks for all your neighbors. Right, you're able to do that in parallel extremely fast. And if you have that infrastructure, then you can pre-process and you can do this pretty quickly. And then similar to what I showed before, right, a lot of these kind of CPU compute can be hidden behind the GPU. Right, while the GPU is doing the stuff for the current mini batch, your CPU is already doing all your random walk for the second mini batch. So as long as your CPU runtime can be hidden by GPU, you don't even notice that there is this random walk happening under the hood. Yeah, thank you.